Probability, it's a continuation of combinatorics. It's a natural continuation of combinatorics. And let's understand a little bit of what is probability. So probability, the area of probability, the science of probability is the study of non-deterministic events. So if you think about life is not deterministic in many things, right? Many variables of our lives are not deterministic. For example, if you want to take a card from a deck of cards, you can't tell with certainty what card will you take, right? So it's what we call, it's a non-deterministic, it's uncertain. If you roll a dice, you don't know with precision, not with precision, but with certainty. You don't know with certainty what the outcome will be. If I ask you what is the weather for tomorrow, you will do an estimate, right? But it's uncertain. You will do your best. You will try your best to be accurate, but it's uncertain. As well as the results of the outcomes of an election. So there are several variables that are non-deterministic in our lives, or what we call events, right? We can call like the event of taking a deck of cards, the event of rolling the dice, the event of the weather for tomorrow, the event of an election. So probability, we will analyze what is more likely to happen, because when I ask you what's the weather for tomorrow, you, based on your what you're experiencing today and a trend for the last few days, you will try to estimate the weather for tomorrow using your sense, using your heuristic sense. You know, like, oh, I think it's more likely to rain because this week it rained a lot, and we are in the fall. In the fall it rains. So you will make it. You will pose a estimate, right? We will answer me what is more likely, what you think it's more likely to happen. And as well as in an election, for example, who is more likely to win? And you have methods to calculate that. And this is actually this is what we call probability. So in probability, we are calculating in a quantitative way, right? So we are calculating the likelihood of something happening, okay? And we will give these numbers, and that's the beauty of mathematics. We're getting something that is totally subjective, and we're going to assign numbers so that we can compare things, for example, right? So there's a chance of rain of 80%. What does that mean? What the number 80 means, right? So when we study probability and we learn how to do these calculations, we also learn how to understand probabilities when we see them coming up on the television or on any other estimate that we're doing. Okay, so well, ultimately what we're doing, we're mathematizing our ideas, right? This mathematizing this sense of likelihood that we have in our lives. Okay. And just to tie one topic to the other, the reason why we study combinatorics or counting techniques before probability is that because while we're doing an experiment, right? So let's say that we're doing an experiment where I have to draw a card from a deck of cards, right? And I want to know what are the chances? What is more likely to happen? Or what is the chance to get a 4 of spades, right? For us to calculate this, to mathematize this concept of what's the chance of this thing happen, we need to know all the possible outcomes. And so in a deck of cards, we know that we have 52 possible outcomes because we have 52 different cards. And I'm asking, what's the probability of an event, or what's the probability, what's the chance of selecting a four of spades, right? So to do this calculation, to mathematize this concept, I need to know how many possible ways I can have an outcome, to then see how likely is one particular outcome. So we call this particular outcome the event. So let's say four of hearts, I don't know. And all this, so this particular event in my experiment, which is drawing cards from a deck of cards, I want to know what's the chance of this event happening, right? So I need to count things. And that's where the combinatorics or the counting tools come in. For a deck of cards, this is very easy to see that's 52. We already know. You can just read in the box of your deck of cards. There are 50, or you can even count them out, 52 cards. But there are other problems where we will have to rely on the theory we saw about groupings, about sampling without replacement, or permutations, to kind of define the number of possible outcomes I have in my experiment. Okay, so first of all, let's start setting the stage for probability. And first, we need to first understand what is a sample space. Okay, so we define a sample space to be a collection of elements, okay, where each possible result of our experiment, or outcomes, right, is represented by one element of this sample space, okay? And secondly, that no result of our experiment is represented twice, okay? And for the elements in this thing that we call sample space, we call outcomes or sample points, okay? All right, so it's very wordy and it's very hard to interpret without an example. Let's start with an example, okay? So suppose our experiment is observing the weather for tomorrow, right? Our experiment is observing now, but estimating, sorry, not observing tomorrow because we can't. Estimating the weather for tomorrow. This is our experiment. What is the sample space of this experiment? Well, the definition says that the sample space is a set of all possible outcomes of this experiment, right? So let's go back. It's a collection of elements where all the outcomes, so the elements of a sample space are all the outcomes of our experiment, okay? So let's say we can see that it will be sunny tomorrow, it could be cloudy, rain, it could hail, it could snow, or it could be foggy, okay? So I have 1, 2, 3, 4, 5, 6 possible outcomes. So this set, this collection of elements, this is the set, this can be understood as a set. Each element of this set, which we call the sample space, is called an outcome. So this is one possible outcome, this is another possible outcome, this is another possible outcome, this is another possible outcome, this one's another possible outcome, and this one also is a possible outcome, okay? Or we call it sample points. So from my experiment, I have 6 sample points, or six sample points, or 6 outcomes. Right? This is what this is all that it's possible to happen, right? So although it's uncertain, I know that it has to land, in one of these 6 elements. It's uncertain, but not free to be anything that we want. Okay? Right. So this is the definition, right? The elements of a sample space are what we call all the possible outcomes, but it has 2 properties as well. Each possible result of our experiment is represented by one element of the set. So, okay, this is a possible result, and it's one element. This is another result. This is one other element. Another one, another one, another one, another one. So all possible outcomes, all possible results are represented by one outcome in particular. And, oops, sorry, where is it? Here. And the second property is that no result is represented twice. So I'm not representing any result twice, so this is a sample space. Okay, let's work another example together. Let's say that I'm going to toss 3 coins, right? What is the sample space of this experimental? A possible sample space, because we will see in a few moments that we can have more than one sample space. But the most simple sample space, right? So I have 3 coins. So let's put it this way. I have, well, let's do a tree. I have coin 1 as the first decision layer. It can be heads or tails. Let's say that the first one came heads. Then I can have a second one being heads or tails, as well as here. And then for the third one, we have heads, tails, heads or tails, heads or tails, and heads or tails. So I have a total of 8 outcomes, 8 possible outcomes, right? So let me set a space set, right? So let me do it like this. It will be heads, heads, heads. It's one outcome. Then heads, tail. Heads, heads, tail, right? Then heads, tail, heads, then head, tail, tail. So I'm just transcribing the paths here. Then will be tail, heads, heads, tail, heads, tail, 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 head, and finally tail, tail, tail. Okay, so we have 8 possible outcomes in this sample space. And let's say if the properties hold, so each possible outcome is described by an element of the set. It is true. And I have as a second restriction, or as a second property, that no result is represented twice. Okay, yeah, so this is a sample space. Now let's consider another example. Now, suppose 3 coins are tossed. Are the following sets a sample space? Okay, so let me copy the most basic sample space here, which is just a sequence of results, right? It's all possible results. And by the definition, a sample space is a set where every result is represented by an element or a sample point or an outcome. And no result is represented twice. Okay, so it might be that I'm not interested in saying what's the chance of heads of this particular combination here, HHT. I want to know the chance of having two heads up, right? So I have, it could be this particular result or this or that. So I can tailor my my sample space depending on the experiment I'm doing. Okay, so let's check if this is a sample space for this experiment of tossing 3 coins. Obviously, this one is the most basic one, but we can tailor it differently. So what are the chance? So what the first element here, the first sample point or the first outcome, is saying that I had 3 heads turned up. Well, let's see. This is true. This can be represented by that. So, okay. Then we have 2 heads turned up. So these are 2 heads turned up results. So these results are represented by this element here, right? Oh, I forgot the pink one. This pink one here. And exactly 1 heads turn up. So this, and that, right? So it is true that the results are being represented by the sample points, but I miss one of the properties. The first property here is, if you go back, said that each possible result of our experiment is represented by an element. And this is not what's happening here. This result is not being represented by any element in my sample space. Okay? So this is not a sample space. To be a sample space, this should be 3 heads up, 3 heads turn up, then exactly 2, I'm gonna do it a little bit quicker. So exactly 2, oh Jesus, exactly 2 heads turn up, exactly 1 head turn up, and we're missing 1. So I should describe this outcome as exact or no heads turn up. Okay, so if this is a sample space. And why is that? Because then the pink part is here, the blue part is here, the green part still here, but the red part that was missing is now here. So now if we take a look at the definition, all results, right, are represented by all results are represented by elements of my sample space, okay? And no results are represented twice. So if you have this blue result here, this one here, it's not being represented by 2 different elements of the sample space, okay? So this is a sample space. And this is useful because I might be asking myself, what's the chance of 2 heads turned up? I obviously can do the calculations and use like the combinatorics and count all the possibilities using this, the most basic sample space, which is the sequence of choices. But sometimes it's very useful to analyze all the possibilities using some different wording. And don't worry, we will see when we should use this, when we should use different wordings, when we should pose the sample space differently than the sequence of events. Okay? Now, let's do another exercise to check if this is a sample space. So in the same problem of tossing 3 coins, is this one here a sample space? Well, I'm wording it like this. 3 heads turn up, exactly 2 heads turn up, exactly 1 head turns up, and at least 2 tails turn up. Okay? Well, let's see. We already saw that this first part, the pink part, is here. So this heads is 3 heads turn up. We saw that the blue one is here, exactly 2 heads turn up. Then we have exactly 3 heads turning up here. Exactly 1 head's turning up. Ooh, it's a green one. Sorry. Exactly. It's not working. Okay. So exactly 1 head's turned up. And then we had this red one. Let's see if we can. So we represented everything but this red one. Let's check if this red one can be represented by this one. So at least 2 tails turn up. Well, it is true that this red one that is tails, 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 right? It is true that this is at least 2 tails turned up. It is. So it is true. But we have a problem. Why do we have a problem? Because this red also represents this one. Because this one also has 2 tails, at least 2 tails. And this one has 2 tails. And this one has 2 tails. So right now, although we have every element being represented by sample points or by outcomes of my sample space, some results are being represented twice by the sample points. So for example, this result here can be represented either by the green sample point or the red sample point. This one as well. So this is not valid. We cannot have a sample space that has that violates this rule. Okay? Because we need to, if we do this, it is as if we're counting not 8 possibilities, but 8, 9, 10, 11, right? We're representing 11 things, and this is not true. The only possible outcomes of this experiment are 8 different things and not 11. So when we pose, so this is not a sample space. When we pose our sample space, in other words, with other wordings than the sequence of choices, we need to be careful. We need to be careful to make sure that we are guaranteeing that this is a sample space, right? If we were to use this one here, we would be missing TTT, right? So we would be considering, we would be counting only 7 possible outcomes. So to do it right, we need to add this thing. And in this one, if we use this final thing here, this final wording here, I would be counting not only 8, but I would be over counting 1, 2, 3. So 8 plus 3, 11. I would be counting 11 possible outcomes. And this is not true. So to make this one, again, a possible sample space, I could I have the I'm not going to write it again. So I have the pink, the blue, the green, and then this red has to represent only this guy, right, that was missing. And this would be, for example, at least three. At least three tails, right? Or it could be no heads turn up as well. It depends on your wording and what you want to word it. But you cannot violate the two rules, okay? All right, so often we use S to denote the sample space. So often we use this as S. This can be an S too. This can be an S. And we will also denote an event, right, by a capital letter. Okay, so what is an event? Well, an event is a subset of that sample space. It's something of that sample space. For example, if we go back, well, what's the event? The event is, I want to see I want to estimate the chance of three heads turning up. Well, so this is an event. It's a subset. Or I could ask, what's the chance of having three heads turned up and two heads turned up? It's also a subset of the set S. Okay, so the event is the question, is the thing that you want to calculate the likelihood. Okay, and it could be it has to be a subset, so it has to be something that is within the possible outcomes, right? So it has to be a subsample, a subset of this sample space. Okay, for example, if you have the event of rain, sunny, hail, snow, E can be the event that is precipitation. Okay, so let's do this one. Let me copy again. I did not copy in beforehand, so let me copy. This is the most basic sample space, which is the choices that I have, right? And the event of precipitation is a subset of this. What could be the precipitation event? Well, it could be raining, it could be rain, hail, or snow, right? Why is that? Well, because all of them involves precipitation, right? So maybe what I want to do is, what's the probability of having precipitation tomorrow? Well, you will have to account for outcomes of rain, hail, and snow. So the event is the subset I'm interested in, and it has to be a subset of all my sample space. Okay? And we will do several exercises so that we can bring this to muscle memory and to be so that you can be more used to do this kinds of things. So that we can end this lesson, I'll just leave you with this. It's a practical tool to check if you have a sample space, right? A practical tool using arrows. So again, let's go back to the tossing of 3 coins. Okay, and the thing is, you need to match each result to the sample points in the set, and just see, right? So I used the markers. Sometimes you don't have the markers with the colors, so you can draw arrows. But it's as I said in some previous lectures, it's really good to have different color pens in your tests when we're studying probability. So I'm drawing a sample space with this wording. I'm just interested if I want to know if more heads, for example, I could be interested in an event where more heads turned up than tails, or more tails turned up than heads. Okay, so I'm posing my sample space as these two possibilities of these two outcomes, and let's analyze if this is a valid sample space. So HHH means that more heads turns up than tails. Heads, it's this one, right? This one as well has more heads. And then more tails, we would have this one, this one, this one, and this one. So indeed, all elements are represented by outcomes in the sample space or sample points. And I don't have two arrows coming out of the same result. If I had something like this, right, then I would be violating the second rule, which is one result can be represented twice. I would be overcounting my possible outcomes. So yes, this is a possible sample space, and I can phrase this like this. Okay. Now, here's a question: if I were to toss 4 coins, would this be a sample space? Well, we could draw the tree and then put all the all the sequence and of the results, but I will invite you to think about this result here of tossing 4 coins. Well, let's think about this result. This result is not represented by the first sample point or neither by the second sample point. So this is not a sample space. We're missing this guy. So to be a sample space, we would have to heads and tails are turns up equally. Okay. So you will have a bunch of exercise to think about this. And again, this is just the foundations of probabilities. So let's recap really quick. Probability is mathematizing likelihood, and we know that we have an experiment where we have results, right? We have to count all the possible results and transcribe all the possible results into what we call the sample space. And it's not unique. It could be the results per se, like the choices, but we can word it differently depending on what probability question we will be asking, right? But in doing that, we need to take care. We need to be careful, right? We need to care about if every element is represented, every result is represented in the outcomes, or what we call the sample points. And if no result is represented twice, if no result is represented twice. So this is something that we have to be careful. Okay, and we will learn how to use different phrasings and different wordings for representing different sample spaces. Don't worry about this. We will get into that. I just need you to understand the concept of sample space, and that we have to be careful. If you're tossing 3 coins, it might be that you have a valid sample space, but if you're tossing 4, that sample space might need to be revised to be a proper sample space to another experiment. Okay? All right. Thank you so much, guys. Hello. How's everyone doing? Good? Good? Prepared for the tests?
Yeah, totally.
Can we have another review?
Yes.
I was gonna ask Sam.
What?
And also, are these probability slides on them as well?
No, they're not in the test. Is it that way?
No, that was on the right space.
Oh yeah, I'm gonna put it today.
Okay.
Yes. Yeah. After the lecture, I'm gonna upload it. Okay.
What
All right.
Thursday are we able to do more review?
First is the time.
Sorry?
Friday.
It is. Oh, I have no idea my days.
What time is it?
Saturday, yes, Saturday.
At like 6.
7 to 8 on Friday.
Friday, and then we'll be here. So I will give an announcement. I will put an announcement now. It will be on the annex building. You know where like in SA150. Yeah. But I'll let you know through. Okay. So let's let's keep talking about probability. This is the new chapter of the content, chapter 2 of the textbook, which we don't use a lot, but so we started talking about probability on Thursday, and we were saying that like probability is a part of math that we try to mathematize likelihood or the chances of things happening. So things that are not deterministic, things that are actually non-deterministic, meaning that they have chance, they need to be, it is good for us to kind of measure, to quantize this likelihood, right? And we started talking about the first concept in probability, the first major concept in probability, that is sample space, right? So you're doing an experiment where you're observing outcomes of this experiment. So it's non-deterministic. It can be different outcomes can happen, but to mathematize, to make it quantitative, we need to know what all the possible outputs are. Okay, and this is the first step to calculating probabilities. So if you're doing an experiment where you are forecasting the weather for tomorrow, what is the possible sample space, or what possible outcomes there are? Well, it can be sunny is one outcome. It could be cloudy. It could rain. It could hail, and it could snow, and it could be foggy, right? So what we call sample space, and we usually denote sample space with an S, is a set of outcomes, right? So it's a set where the elements are all possible outcomes of your experiment, okay?
Are these lecture notes on our?
It will be soon. After the lecture, I'll upload it, okay? And then we talked about, for example, if this was the last example we talked about in the last lecture, is suppose I toss 3 coins, what is a possible sample space for this experiment, right? And so, and if you notice the question, I'm saying what is a possible sample space? We will see that actually we can reword sample spaces and we can have more than one. But for example, what is a possible sample space for tossing 3 coins? Well, you can have, each coin has 2 outcomes, right? Heads or tails. But if you're considering your experiment as having the coin tossed 3 times, one possible outcome would be tails, 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 right? The other outcome would be heads, heads, heads. Another outcome would be tails, heads, tails, and so on. And we know how many possibilities there are because we know counting, and we know that this is a selection without replacement with three layers. So this is 2 to the third or 8 possibilities. You can kind of do it by hand because it's a simple example. So we have heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, head, tails, tail, tail, heads, tails, okay? So this is the sample space, the most simple sample space, I would say, because it's actually the results of your experiment in the sequence of things that happen. But we can sometimes we're not interested in saying, okay, what's the chance of having tail, heads, right? So because that's the questions that will arise in probabilities is what is the chance of having tails, heads? So you know all the possible chances, and then you will have to do a calculation, right, to kind of mathematize this value. But sometimes we're not interested in a simple point, in this sample point outcome, a single point. We are interested in questions such as what is the probability, or what is the likelihood, or what is the chance of 3 heads turning up, or exactly 2 heads turning up, or exactly 1 head turning up. So if you think about it, let's say, let's take this pink phrase here, this sample point in the sample space. This element is an outcome. It's exactly 2 heads turn up. Actually, I'm talking about this single outcome and this and this, right? Because those outcomes have exactly two heads coming up, right? So you can, maybe sometimes you're not interested in a single outcome, but like a combination of them. And you can change the wording of your sample space to make it easier. So for example, in this sample space here, we have the pink part that's regarding two heads, right? We have the green part here that regards three heads, so this is a single point, it's okay. And then we have another, I'm going to take the, let's see, this one. No, too close. Blue. Okay. And then we have this one, exactly one head, which is this one, and this one. Okay? Now, I'm not calling this S, this tentative sample space, right? I'm not calling it S because it's actually not a sample space yet. And why is that? If you go back a few slides, we defined sample space to be a collection of outcomes that each possible result of our experiment is represented by one of the elements of the sample space. Okay? So putting in other words, each result from our experiment, each outcome has to be represented by an element of the sample space. If you go back in our example here, there is an outcome that is not being represented, right, by a sample point. Which one is it? Yeah.
the T, right? So this guy here is not being represented into the sample points. So this is actually not, it cannot be a sample space. This is kind of wrong, but we can make up to it, and we can kind of add a condition here, a new element, where we say no heads turn up. Now this is a sample space. Okay? So again, a sample space is a collection of outcomes from an experiment. It can be the basic one, like that has all the outcomes individually, or you can come up with more interesting sample space depending on what question you are posing. But be careful, because your sample space has, even if you're kind of mixing or combining outcomes, all of the outcomes needs to be represented. You can't miss any of them, okay? Because if you think about of an experiment, the sample points have to have every possibility that comes out. If you're thinking about the number of heads, what are the possibilities? 0 heads, 1 head, or 2 heads, right? Or 3 heads. So we have to account for these 4 things. Otherwise, we're not aware of all the possibilities that we have. Okay? Cool? Now, there's another property of sample spaces. If you go back to the properties of sample spaces, this is the property, is that no result is represented twice. Okay? So your sample space can't represent one outcome twice. Let's think about that. In this first sample space here, that's true, right? I'm not representing an outcome twice. So for example, this outcome, this pink outcome here, HHT, is just represented by the pink. It's not being represented by more than one sample point. Okay? So this one is okay. It kind of complies with both rules, where every point is being represented. So every point is represented, or every outcome is represented by a sample point, and also a outcome is not represented twice, just once, right? Now let's take a look at the next possible sample space here. Let's say that somebody asks you, okay, I'm coming up with a new sample space because I'm running an experiment. Can you check if this is right? Well, let's check. 3 heads turn up. Well, 3 heads turn up is the green. It's the same thing as the green, right? So I'm just going to keep the same color code. This is the green. Then the pink is also here. Exactly 2 heads turn up. So here's the pink. Then there is the blue. There's the blue here. Exactly 1 head turns up. So if you go to the single outcomes, like the most basic outcomes, you can see that the blue is HTT, THT, TTH, because only 1 heads turn up. And then whoever did this sample space, whoever proposed this sample space, also consider this element. At least 2 tails turn up. Okay? So let's find what this means in the basic thing. I'm gonna take a dark blue. So at least 2 tails turn up. What outcomes would be part of this element? Well, it would be at least 2 tails. This one, this one, this one, and this one, right? So in the end of the day, you can think about this. Well, every outcome is being represented, right? Nobody is missing. If you can take a look here, everything is being represented. So this is green, this is pink, pink, blue, blue, blue. Everybody is represented. But what is happening here that's wrong? What's happening here that it's wrong? Yeah.
Some are represented twice.
Yes. So for example, this guy here, it's represented by exactly 1 head and at least 2 tails, right? So this guy here, I'm talking about this guy. If you look at it, you can see that having exactly 1 head is actually the same as having 2 tails. So in the end of the day, if you use this sample space, okay, you are overcounting the possibilities. In theory, you would have 8, right? 1, 2, 3, 4, 5, 6, 7, 8. You would have 8 possibilities. But if you leave it this way, you are in the end, under the hood, you're considering 1, 2, 3, 4, 5, 6, 7, 8, and then count again the dark blues. 9, 10, 11, 12. Right? And then your calculation of likelihood will be wrong. Okay? Because you don't have 11 things that will come out, 12 things that will come out. You only have 8. Okay? Yeah.
So the last 2 were considered the same?
The last 2?
Yeah.
This and this? Wait, where's my mouse? This
are
and
you saying that like at least 2 tails and exactly 1 head, like come to the same category?
yeah,
Okay.
yeah, exactly.
So
So
like, would we have to just change it to like, if it's like at least 2, would that have to be then like, because if it's 2 tails, then exactly 1 head would be it, but like at least 2 implies that it could also be 3.
yeah, so we're gonna see how to fix it. Okay. We're gonna see how to fix it. But in the end of the day, what's the problem of this? So this, every outcome is represented by a sample point. Okay? But an outcome, so some outcomes are represented twice. Right? That are the light blues and dark blues. So what would we do to make this sample space as a proper sample space, right? So if you think about all the other sample points are talking about heads, right? 3 heads turning up, 2 heads turning up, which is the pink, and 1 head turning up, which is the blue. Yeah.
Would we just do like no heads turn up again?
You can do no heads, or if you want to pose it as tails, what should you say? At least 3 tails, right? So then you would be considering only this as the dark blue. Okay, so at least 3 tails, or the same one as no heads turning up. Okay? So in the end of the day, the takeaway is sample space, it's just a collection of all the outcomes. Don't forget that sometimes if you're posing it in a wordy way that kind of is not the basic structure, just be careful to not to forget any outcome or not to overcount any outcome. Okay? And that's it. Questions about this? Yeah.
How, so like, I kind of got lost with that. So you don't represent it more than once. So like if you have heads, tails, and heads, tails, heads, you wouldn't represent both things if it was supposed to be two heads.
So you're talking about the pink part?
Yeah.
Pink part? You have two outcomes in the pink part, right? So you think about this. These outcomes are represented by the pink part. That's fine. Cool. But if they're represented by the pink and yet another color, then they're being represented by more categories in the sample space.
Oh, then so you can't write it again.
Yes, exactly. Okay. And we will see lots of examples, and we will talk about sample space. You will get the, you'll get used to doing this, hopefully. All right, so let's move on. So we have sample space, a collection of all the possibilities of your experiment. Sometimes it's the basic structure, sometimes you're using words, whatever. S is whatever is coming out of your experiment. Now, all the possibilities. Now we are going to call an event of your experiment a subset of this sample space, okay? And we will often denote by events E, F, capital P, capital whatever. Because, again, if it's a subset of the sample space, we call a capital letter, because subsets are sets, capital letters are sets. Okay, so I will give you an example, because usually events can be described verbally, okay, using words. So I'll tell you this: the event here is having precipitation tomorrow. Okay? So this is an event. It's a word, and if you take a look at the event described from this kind of wordy, from this verbal expression, it is actually a subset of my sample space. So for example, what is a precipitation? Well, it can be rain, this one. It can be hail, this one. Or it can be snow. Okay? So usually events are parts of my this is the whole, S is the whole world of possibilities. And E, the event, is I want to ask a question about a subset or a particular case of something. So for example, I could ask, what is the probability of having precipitation tomorrow? So what you want to measure is the likelihood or the chance of these three things, of this subset of things happening in your whole possibility. Okay? This is one example of events. It could be a simple event, such as, what's the of being sunny? Well, sunny is also a subset, so you can ask that question. Okay? Yeah.
Would we just have to write it up like that, or would you want us to actually go through?
You can write the way you want. Like you can write, if you're going to describe it verbally, just use a column, and if you're going to describe as a subset, then just put, as we learned, just put in between bracket the curly braces. Okay, yeah. Yes. Yeah, we'll do some examples. But that's really, we're setting the stage for calculating the likelihood, right? So we have an experiment, we have lots of possibilities as for the outcomes. That is my space, the whole space, the sample space. And I want to select a event inside that sample space, or a sub-selection of that, and ask the probability of that happening. That's what we're doing. Okay? So this is not what I want. Okay. So we set the stage, and we're going to start calculating probabilities. Okay, so we're going to start making this quantization of how something is likely or not to happen. We call probability measure an operator. So in math, we call a probability is a mathematical operation. It's an operation that you do. Okay? So it acts in an event and assigns it a number. Okay? So think about this. A probability is an operator or a black box. Imagine a black box where you come with a cable, and you input the cable with your event. And in the output cable, it gives you a number. Okay? So what's the probability of having precipitation? So I'm inputting into this operation, into this black box, this event that is precipitation, and the probability operator will answer me a number. Well, the probability is 0.2. Okay? That's what probability is. We don't know how to calculate it still, but it is that, right? So probability of an event happening within a sample space is a number. Okay? So given an event, I will answer you a number. What's the probability of event A? A number. What's the probability of event B? I will answer you another number. So probability are numbers that depends on the event. Okay? And this number, the answer of the operation, which we denote as P of E. So P bracket, square bracket of E, it means the probability of event E is a number. This probability, this number, is bounded. It's always bounded. It's between 0 and 1 and cannot be negative. It cannot be higher than 1. It cannot be, right? So we have to be, the number has to be between 0 and 1. Why? Because this is a measure, we're kind of creating a scale where 1, if the probability of an event returns a number 1 to you, it means that the event will, with certainty, it will happen, or it will definitely happen. Okay? If the probability, this operation, you say, what's the probability of this event happening? And this probability is 0. It means that with certainty, I can tell you that this will not happen. So it's the scale is between I'm absolute certain that it won't happen with I'm absolute certain that it will happen. Okay? So when we say, what's the probability of, I don't know, what's the probability of this water bottle being green? Well, this is not random. Like it's deterministic, right? It doesn't depend on randomness. This is green, so the probability is 1 or 100%. 100% means 100 divided by 100 is 1. Okay? So I'm 100% certain or the probability that this is green is 1. Okay? What's the probability of this being red? 0. Okay? So this is the kinds of, and there's the probability in between. Okay? So if you say that the probability of an event is a half, or 0.5, or 50%, which is 50 divided by 100, this will be like, it's a toss of a coin. It's half-half chance of happening. Okay? So here's an example. Let's say that we have a bucket, and inside the bucket we have 3 balls, numbered balls. We have ball number 1, ball number 3, ball number 6. Okay? And I want to talk about an event. Let's make up an event. The event of getting a number that is multiple of 3. Okay? So I kind of described using words, right? This is like this. I kind of described using words, but I also could have described using the subsets. What are the numbers that are multiple of 3? Well, 3 is multiple of 3, and 6 is multiple of 3. Okay? They're all divided by, divisible by 3. Okay? So what am I asking is the probability of this happening. I could ask, what's the probability of E? Okay? Meaning that if you think about a system, a computer that calculates probability, you would be inputting this event into the computer, and the computer would be spitting out a particular value, right? A value of between 0 and 1. Okay? We're not going to calculate still. Wait. So now let me ask you something. What is the probability? Just lost my pen. Just wait. What's the probability of having an event that is actually this? What is the probability of having drawn a ball 1 or 6 or 3? Yeah. 1. Why?
Because there's 3 things total, and we're saying that you could pick any 3 of them.
Yes, exactly. So when the event matches the sample space, right? So you're talking about drawing or doing an experiment that kinds of, all possibilities are, you're playing with all possibilities. The probability of having that is 100%, meaning that something will have to come out of that bucket, right? Either 1, either 3, or either 6. So if I tell you, what's the chance of getting 1, 3, or 6? Well, one of them you will have to get. So I am certain that this will happen. Okay? So this is one of the properties of probability, is that it's that the P of P of the samples point, or P of of your the probability of having at least one thing of your whole possibility is 1%. Okay? 1%, no, sorry. It's 100%, or 1. Okay? So something will happen. I am certain that something in the sample space will happen. You can think about this. So at something inside the sample space will certainly happen. So whatever is in your sample space, this will happen. Okay? Now, there's another property of probabilities, that is this famous equation here. And you will see that this equation is actually, you don't need to remember it, it just makes sense. Let's go back to the bucket example, okay? I'm going back to the bucket example. Now imagine this. If E is the getting a number multiple of 3, I'm going to ask you a question of midterm 1. What is E complement? What is E complement? Getting a number that is not multiple of 3, right? Getting a number that is not multiple of 3. In this case, which number is not multiple of 3? Is 1, right? Now, when we have these kinds of events that are complementary or contrary, we can say that, for example, whatever probability I have for having a number of multiple of 3 plus the probability of having a number that is not multiple of 3 must be how much? So the chance of picking a multiple of 3 plus the chance of picking not a multiple of 3. It's 1. Why? Well, because either you get a number multiple of 3 or you don't. So it's 100% sure, I'm 100% sure that one of these events will happen. Event E will happen or event E complement will happen. So the sum of probabilities has to sum up to 1. Okay, so this is another property. If I tell you, oh, the probability of having this is 2/3. You don't need to understand why right now, but I'm just telling you, it's 2/3. The probability of having a multiple of 3 is 2/3, right? Well, you know that having all the possibilities inside the bucket would be 1, right? So the probability of not having these numbers need to sum up to 1. So if you have 2/3, the probability of not having a multiple of 3 will be 1/3. Okay? Because either you will have or you won't have. Okay? So if you're 100% certain that one ball will get out the bucket, and you have 2/3 that it will be multiple of 3, the rest is the other ball that is not multiple of 3. Okay? So this is the other property. And some people like to write this property as this. It doesn't, I really don't, it doesn't matter. It's just same equation. Just people sometimes like to kind of subtract this guy to the other side. It's the same equation, it's the same concept that either E or not E will happen. So the chances of their happening have to be 1 because either of them will happen. I am certain that or this or that will happen. Okay? Questions about this? Yeah.
So, what's the difference between, like under 3, there's 2 formulas, like it's the same thing, it's just written
Mm-hmm.
So like you don't care which we use?
No. It doesn't. You will see that you won't even need the formula. You will kind of the concept of that the having some part of the sample space and having the complement is they have to sum to 1. It will get better. Like
In the second part at the bottom, it's 1 minus
P of E. So the how you get from here to there is you take this P of E and you subtract to the other side, and then you land in the second formula. Right? It's the same. It's the same thing. Okay. More questions? Okay, so let me ask you this. I have a bucket, and inside my bucket, I have a red ball and a blue ball. Okay? And I mean, this blue ball here is a little bit heavier. It's a little bit bigger and heavier. So it's usually like, and so I'm telling you that I have a probability of getting a red ball. It's a bigger probability. It's not half a half, right? It's, I don't know, 0.7. Okay? I'm telling you that. I just calculated. You don't know how I did it, but I calculated the probability, and it's 0.7, meaning that I'm 70% sure that this will happen. Okay? I'm assigning numbers to my subjective feeling of that will happen. What is the probability of drawing the blue ball? What? 0.3. Why? Well, because drawing blue or red is 1, right? Like, you know that you will, in the end of the day, you're 100% certain that drawing a blue, the chances of drawing a blue and the chances of drawing a red are 1, right? That's your experiment. Your sample space is blue and red. So it's 100% sure that this will happen. If you have 0.7 to the red, it means that you're left with a chance of 0.3 to the blue because of this condition here. Okay? So if you have 70% chance of drawing a red, you will have only 30% of chance to draw blue. Okay? That's guided by this equation here. Cool? Questions? Are we good? Okay. Now I'm talking about, I'm assigning 0.3, 0.7, point whatever, and in the end of the day, larger numbers means more likely, right? So if you have P of X bigger than P of Y, or P of R bigger than P of B, it means that, for example, in this case here, the probability of rain tomorrow, it's 2 times the probability of being sunny tomorrow. Okay? So it's kind of linear, right? So when you're talking about 7, so if this was 6, right? And this was, so let me see, if this was 1 and this was 6, this was 9, sorry. Okay? You would say that the probability of drawing a red is 9 times bigger, okay, than drawing a blue. It's really this relationship. It's linear. You will see probabilities as decimals, 0.6. That you can kind of use as percentage. You can always think about decimals decimal numbers as percentages. So for example, 0.6 is 60%. I forgot a zero there. This is 60%. So 0.6 is 60%. Okay, meaning that when you divide 60 by 100, when you divide the number by 100, and this is something that last year I found out that most students struggled with. And so if you go to OWL in the resources section, you will see that there are several videos on how to handle decimals and percentages. So it is very important that if you don't know how to analyze decimals and percentages, that you go through those videos, okay? But any number that you divide by 100 means that you're getting the point here, the decimal here, and you're walking 2 to the left. So 1, 2, which is the number of zeros here, 1, 2, and here is the decimal, okay? So 40% is the same thing as 0.4. You will have to know how to go back and forth with this decimal percentage thing, okay? So if you don't know how to do it, this is a good time to stop and go through the videos, kind of learning how to make this calculations, okay? Another kinds of probabilities that can come out of the operation could be in terms of frequency. So, the probability is that, for example, there is let me rewrite this. So you can say that 7 out of 10 times something happens 7 out of 10 times. You will also find this kinds of ways to pose probability, right? What is 7 out of 10 times in terms of decimals? Who knows? 0.7, right? So this is 0.7. Or what about in percentage? What is 0.7? 70%. Okay? This is we're not calculating the probabilities yet, but we're setting the stage of what is sample space, what is an event, what are what's the probability of having something in the sample space as an outcome? Is 1. If you have one event and the other event is complement, you will have one or the other, so the sum of likelihoods have to be equal to 1. And you can express these probabilities as decimals, percentages, or like a frequency wording. Okay? Questions? Questions? No? Okay, so the last thing that we have to, know is that for an event, the probability of the event is the sum of probability of the individual outcomes. So for example, I have an event that is drawing a ball A and a ball B from a bucket. Actually, it's when you see this comma here, this is actually telling you this is this event here is the element A or the element B, okay? It's the same thing. So what's the probability of the event? Well, it's the sum of the individual probabilities. Think about the example we talked about in the precipitation. What would be the probability of the precipitation? Well, the probability of precipitation would be the probability of having rain plus the probability of having hail plus the probability of having, what was it? Snow. Why? Well, because the precipitation event was equal to rain or hail or snow. So this is another rule of probability. If you have an event that combines outcomes, right? The probability of that event is just the individual probabilities. Okay? Always think about the precipitation example, that it will be more clear. Like precipitation, what do you account for precipitation? Well, I account for snow, hail, and rain. So whatever probability is rain, whatever probability is hail, whatever probability is snow, I will sum that probabilities to have the probability of precipitation. Okay? So now, having we discussed all of this, this is a first exercise for you guys. What I want, I forgot to, this is from the other slide. I want you guys to calculate. I give you, so we're not calculating the likelihood, the measure of probability. I'm just using the property. I know how to calculate probabilities already. We will know in short soon. But I'm giving it to you. It's given. The probability of A, or drawing a ball with letter A of my bucket, is a half. Probability of B is 0.3, and the probability of C is 0.2. So I have a bucket. You can see that my sample space has ball A, ball B, ball C, ball A, ball B, ball C. And my event is, I want to have, what's the probability of drawing A or B? Okay, so that's what I'm asking. That's what we should do now. What do you guys think it would be? 0.8. So it's A, yep. Wait. Why? Well, we're using the property. We're using the property of probabilities where, well, my event is a combination. And whatever individual probabilities I have, I will sum that up, right? Because my event is a combination of that single points, I will sum up the probabilities of those individual points. So if my event is A or B, the probability of my event is actually P of A plus P of B, which is 0.8. So this is P of A plus P of B. This is 0.8. Okay? Now, what if I ask you this? What is the probability of the sample space? Meaning, what's the probability of taking A or B or C? 100%, right? It's 1. Well, actually, if you apply the rule, the sample space is it's itself an event, right? Where you have A or B or C, right? And you know it's 1%. Let's check if this is right. Probability of A is 0.5 plus the probability of B is 0.3 gives you 0.8 plus the probability of C gives you 0.8 plus 0.2 gives you 1. Okay? So you can find this property of that, the probability of the sample space being equal to 1 by using the individual points, right? Summing all the individual probabilities from your sample space you will have 1 as well. Okay? Questions? Yes or no? Good? All right. I'll give you guys 5 minutes to try to solve this problem. This is the first problem using the properties of probability in more depth. But it's not difficult. Go. Let's try. Five minutes. And then I'll solve it for you. Okay. Does anyone have an answer? 2/3. Yeah, 2/3. Yeah. 2/3. 2/3. Okay. So let's solve this. That's good. Good. Great. So I have a bucket or whatever or experiment. It can have outcomes A, B, or C. And I was giving the probabilities already, right? So I was giving that the probability of drawing an A or having an A as outcome is 1/3. The probability of drawing a B or having a B as an outcome is 1/6. And the probability of C or drawing a C is a half. Okay? First of all, if you sum up the probability of A plus the probability of B plus the probability of C, how much it needs to sum up to? 1, right? Because it's everything. It's the probability of having or A or B or C. Well, you will have one of them, so it's the probability of 1. Okay? So if you sum up 1/3 plus 1/6 plus 1/2, this needs to be equal to 1, and it is. Okay? Now we have an event of the event is drawing A or B. And you have another event which is drawing A or C. Okay? Now, again, events are subsets. Events are sets. So this here, what is inside the square bracket here, right? This is an event as well. It's an event that we could call, I don't know, G. It's the combination is a set operation with E complement union F complement. Okay? And the question is, what's the probability of G? Oh, by the way, you will find probability PR or P. Some people use P, some people use PR. Doesn't matter, right? So it's fine. So, okay. So the question is, what's the probability of G? Let's find G then, right? Let's see who's G. Well, G is this set. So who is E complement? Well, E complement is whatever is in the set S, whatever is in your sample space, but it's not A or B. What is it? Yeah. No. I'm saying who is the set E of E complement? Who's the set? Who is inside E complement? Yeah. C. Right? It's not A or B, so it's C. Union with who's not in F? Well, A and C are in F. Who is not in F? B. So in the end of the day, you're talking about a set that is given by elements C and B or B and C. Okay? And we know how to calculate probabilities of an event that is a composition of outcomes. We know that when an event is a composition of outcomes, you just take the probabilities individually, right? So the probability of G will be equal to the probability of C, and it was given to me, it's a half, plus the probability of B, which is 1/6. Okay? This is one way of doing it. There's other ways of doing it. But so you have to know how to work out these fractions. You will have to know this for the tests, right? And for the quizzes. You will have to know how to get out of this kinds of addition. So if you don't know, just there are resources in the website so that you can learn. But for example, the way I like to kind of like do it is, well, there are people that multiply the denominators and kind of say like, oh, 12 is a common denominator because it's 6 times 2, and then works that out, right? But this is also like 3. You can think about this first term here as 3 over 6, right? Because if you have 3 over 6 and you divide up and like the top and bottom part by 2, it results in 1/2, right? So you can, or you can think about this: multiply by 3 in the numerator, and 3 in the denominator. You're not modifying the number because we're multiplying the numerator and the denominator at the same time. So it's the same thing as 3 over 6 plus 1 over 6, and then it's kind of easy, right? Because it's the same denominator. You have 4/6 or 2/3. Okay, so this is what the kinds of problems we will see. There is another way to solve this. Maybe some of you used it. Is like when you could do the probability of E complement, which is like the probability of where is it? C, right? Like the complement of having A plus B. So you take P of A plus P of B minus 1, right? Plus the probability of A plus C minus 1. Whatever. You can use whatever you think it's good. Okay? Questions about this exercise? Yeah.
Does everything in the sample space always equal 1?
Yeah. When you sum all the probabilities of all the individual samples points, this must sum up to 1. It's a property of probabilities. It has to. If it's not summing up to 1, that's something is wrong. Something is wrong. Okay? It has to sum up to 1. Cool? All right. Thanks so much, guys.